I don't. Okay, so let's start with number one. I just read the question. You can read that on your own on page 524. But basically, what you have to do in chemistry when you're solving problems is you have to figure out what's given and then solve for what's not given. Sometimes, especially with the ideal gas law and the other things that are related to it, like Boyle's law, like Charles' law, like the ideal gas law, like Henry's law, they're going to give you everything in the problem. They're going to tell you what all the variables are except for one. And then before you do anything, you just use algebra to put everything on the other side and solve for the one variable that's left. Then it's just simple plug in. So let's look. Here's what we know. The solubility of a gas is, let's see, what is it? Solubility of a gas in water, and we'll call this situation one. The solubility of a gas in water is, and since it's situation one, I'm going to put a sub one right there. So it is 0.16 grams per liter. Now, if you look at your book and compare to what I wrote, you can see that I wrote it as a vertical up and down fraction. But if you look at the units, when you type it, it's easier to do it with a slash, which is confusing for some people. And it's better to do it like this, especially if you're using dimensional analysis. Another thing to note, I haven't even gone to, like half, I haven't even finished half of the sentence yet. But another thing to notice is that you have two significant figures, and that's what your answer is going to be in. Okay, so here's the second part. The second part is 104 kilopascals. So that's the pressure. And remember, it's a cursive P is better because a capital P means something else. And so P sub 1 is going to be 104 kilopascals. Remember that pressure can be measured in different ways. Can be measured in torrs. It can be measured in millimeters of mercury. But in order to use this equation, you need your pressure to be in kilopascals. So if you ever get a situation where you're trying to use Henry's law and you have a pressure, but it's in torrs or it's in atmospheres or it's in millimeters of mercury, you're going to want to convert it first over to kilopascals. That's not a hard conversion. You can even ask Siri to do that one if you wanted to. Okay, so that's the first sentence, S1 and S2. So it says, what is the solubility when the pressure of the gas is increased to 288? So they're asking for the second solubility. So you're going to solve for S2. And the pressure of the gas is increased to 288 kilopascals. Oops, I didn't say what that was. P2 is equal to 288 kilopascals. All right, so, excuse me. Henry's law of solubility is S1 over P1 equals S2 over P2. So using algebra, all you got to do is solve for S2. So you want S2 all by itself. And to get S2 all by itself on either side of the equal sign, I need to get rid of this P2. That's it in the bottom of this fraction. I just multiply both sides by that 2's should be down there, P2. And I multiply both sides by P2, P sub 2. And so these will cancel out. I'm left with S2 by itself, which is what I wanted. So to clean this up, I'm going to say S2 is equal to S1 times P2 over P1. So that's just solving for this variable. Again, you have 4 things. They're going to give you 3 of them. You solve for the last one. That's almost all chemistry problems, something like that. So now it's just a matter of filling in. So I'm going to go over here and say S2 is equal to 0.16 grams per liter times P2, which is 288 kilopascals. That's all over P1, which is 104 kilopascals. Okay, and what we're left with is, if you look at the units, you can see what's happening. The kilopascals are going to cancel each other because you have one on the top and you have one on the bottom. So you're going to cancel those out. And then you're left with G over L, which is a solubility. How many grams of something will dissolve in a liter of something else, usually water? So this is a unit, which has to do with solubility. So that makes sense. So we can now go and multiply that out. So let's do it. 288 times 0.16 divided by 104.
It's about 0.443.
0.443. Okay, so remember we only needed 2. So that's going to be 0.44 grams per liter. Okay, there you go, 0.44 grams per liter. All right, which then I'm looking at the answer key, and my answer key doesn't tell you how to do it, but we do have the same answer, except they expressed it in scientific notation, which you don't have to do when it's something like this. You know, if it was 0.0000044, then I would say, yeah, do it as a scientific notation. But if not, then that's the answer anyway. So I would accept that. I wouldn't expect you to do scientific notation unless you had a multitude of zeros. So as always, we box our answer and we show our work. And that's 1 out of the 9 questions. So see how slow sometimes you are with chem stuff. Okay. All right. Sam, I have 2.3 from you. I don't know what that is. You probably did that a long time ago. But did I mess it up somewhere? I got the right answer. I don't know. Okay, so that's number 1. Let's go to number 2. Number 2 is another problem, the same kind of thing. Let's see. Turn a page, go to number 2. Number 2 on page 524 is a gas has a solubility in water at 0 degrees. And if you look at the question, let's just read the whole thing. Of 3.6 grams per liter at a pressure of 1.0 atmospheres, what pressure is needed to produce an aqueous solution containing 9.5 grams per liter of the same gas at 0 degrees Celsius? Okay, so temperature is constant, it doesn't change. So that's the way they stated it at that time. In number 2, instead of saying, assume the temperature remains constant, they told you the temperature before and the temperature after, and it didn't change, so you know that it's constant. All right, the solubility in water at 0 degrees Celsius of 3.6 grams per liter. Okay, so that's the first solubility. It's 3.6 grams per liter. And again, you can see there's 2 significant figures at a pressure of 1 atmosphere. Pressure of 1 atmosphere. Now, the thing is that I said earlier, if it's in kilopascals, great. If it's in torrs or if it's in millimeters of mercury, you got to convert. Except the thing is, if they give you both of the pressures and they're the same unit, you can see that they're going to cancel out. It's just you have to make them the same unit, is what I was meant to say. So solubility and pressure, and then at what pressure, that's P2. So P2 is what you don't know, is needed to produce an aqueous solution containing 9.5 So it's in water because it's an aqueous solution. That solution 2 is equal to 9.5 grams per liter. Again, with the algebra, we got S1 over P1 equals S2 over P2, solving for P2. Okay, so you could cross multiply like that. So you get S1 P2 equals S2 P1. Okay, but what you want is P2, so you got to get rid of that P2. So divide both sides by S1. These cancel out. You get P2 is equal to S2 P1 over S1. Yay. Okay, so then to get P2, just fill the blanks in. So S2 is 9.5 grams per liter. Hang on just a second. Okay. So I just got an airport update, so I'm going to keep going. You got 9.5 grams per liter for S2. P1 is 1 atmosphere. Oops, that's a 1. 1 atmosphere over S1. S1 is 3.6 grams per liter. And so you can see the grams per liter. This whole thing is a unit. That whole thing cancels out, and you're left with the pressure that's now in the atmospheres. That's going to be our answer. Our answer is going to have 2 significant figures, and it's going to be 9.5 divided by 3.6. So let's go. 9.5 divided by 3.6.
It's about 9.9483.
9.9. So the answer is 9.9483, which is different than what I got. Let's see. That doesn't make sense. Wait. Oh, I see. Siri misunderstood me. 9.5 divided by 3.6.
It's about 2.6388.
That makes more sense. You always got to go back and say, wait a second, is that right? Does that make sense? Like if someone said, hey, how's the weather today? And you say brown, that doesn't make sense. So you got to look at your answer and say, wait a sec. It's kind of like when you say hi to someone and what is it that often happens, or not often, but occasionally someone says, what's up? And then you say, yes, or something like that. It's just a little awkward goofiness. All right, number 2. So that's number 2. So now we got 1 and 2, and now we should be able to do some of the other ones. Let's crank these out, because like I said, I got to go to the airport, but I do want to make sure you guys get this stuff. Number 3 says, what determines how fast a substance will dissolve? All kinds of things, actually. Now, what is going on in my neighborhood? All right, so temperature could affect how fast things dissolve. What else? How big your chunk is. Like one lab that I do. Did you guys do this lab? You might have done this lab. Anyway, so in one of my labs, I think it's a scientific method lab. We take Alka-Seltzer and time it and figure out how long it takes to dissolve. But then if you crush it, it dissolves much quicker, you know, in the little smaller sizes. So particle size is going to be something. And then if you stir it, it's going to help it go faster. So in the laboratory, sometimes you put a magnet in a beaker, and then the magnet hooks to something in your hot plate that's a spinner. Sometimes you put a beaker or a flask is better in a microbial laboratory on a shaker table, and it shakes it up. So to shake it or stir it, or what's another way to say that? To shake it or stir it would make it go faster. To agitate it, like your washing machine has an agitator cycle where it crunches up all your clothes and make sure everything gets exposed to soap. So that's number 3. Okay, number 4. How can you describe the state of equilibrium in a saturated solution that contains an undissolved solute? All right. Well, it depends. Is the temperature constant? If the temperature is constant, what number is this? Number 4. Okay. How can you describe the state of equilibrium? Well, what that is, it's a saturated solution that contains undissolved. So you have a solution and it's got stuff dissolved in it, but then you have some chunks. Well, why don't those chunks go into the solution? It's because this is already saturated. So no more stuff from the solid, whatever this chemical is, can go into solution. But that doesn't mean it can't be in a steady state, or the other term for it is an equilibrium. So in an equilibrium also, it's true that some things are going into the solid, but some things are breaking off the solid. So there is movement, but that movement of things joining this large solid and things leaving this large solid, that rate is the same. So we sometimes call that a steady state. Because things are moving back and forth, it's not just an equilibrium, but sometimes we call that a dynamic equilibrium. Does that help the questions answer? Let's see. How can you describe the state of equilibrium? It's a dynamic equilibrium in a steady state where the amount of solute, we'll say, the amount of solute and the amount of solute in that crystallizes the solid, the amount of solid. It doesn't, like I said, it can go back and forth, but the total amount stays the same. So dynamic equilibrium in a steady state where the amount of solute and the amount of solid is moving, but it's constant, is equal, I'll say. Right, moves back and forth. So something like that for number 4. All right, number 5, what condition determines the solubilities of solid, liquid, and gaseous solutes in a solvent? Well, the answer is temperature and pressure. So write down temperature and pressure. But temperature, if the solute is a solid or a liquid, then that makes sense. But if it's a gas, that's when pressure comes in. So it's temperature and pressure. How should we say this? Temperature and pressure for a gas, but temperature for a solid or a liquid. Said that way. That's good. It's a good way to say it. 5. So a gas depends on pressure and solubility of, that's good. All right, so temperature and pressure has to do with solubility. That's why in the formula that we already used, it has to be constant temperature. And then the solubility and the pressure is part of the formula for Henry's law. All right, number 6. Name a unit used to express, oh, that's just in our problems. We have grams over liter. So grams over liter is the answer, number 6. So that's good. Grams of what? Grams of solute, grams of whatever's going into the solvent. So if you want to say it in words, it's grams of solvent, no, solute, grams of solute. Let's see, 6. Yeah, that's it. Grams of solute per liter. Another one might be in words, grams of solvent per like a set measure of the solvent. So this is assuming it's an aqueous solution in 1,000 milliliters or 1,000 grams, but you could also have grams in 100 grams of whatever the solvent is, or 100 milliliters of whatever the solvent is. But that's too confusing. Just this is what we use almost all the time. So grams per liter, that's the answer, number 6. So number 7. What determines whether or not a substance will dissolve? Well, it's really what the chemicals are. So it's what, how shall I write that? What the chemicals are. Now what the chemicals are made of. Chemical composition, we'll say. Chemical composition of both the solute and the solvent. So that's a good answer for number 7. It's what they're made out of is what determines number 7, whether or not a substance will dissolve. Okay. Wow, good. I thought I wasn't going to get all these, but I think we're almost there. Number 8, explain what you would do to change a saturated solid liquid solution to an unsaturated solid solution. Well, you can add a bunch of the solvent. So you're trying to go from saturated to unsaturated. It's already saturated. So to make it unsaturated, you just, like if you're thinking of water, because that's almost always what it is, then you're just going to add water to it. And so in this case, the water is a solvent. So you can add water, add the solvent, which is almost always water. It's in an aqueous solution, that's water. And then what's part, well, or you could, how else could you do it? Add the solvent. You could also up the temperature. Like if you increase the temperature, it's like, this is why it rains in the tropical rainforest, and then over the desert, it doesn't rain anymore, because the air, as it goes up in the atmosphere, it encounters cooler temperatures, and cooler temperatures can hold less of the water molecules in the solution, which is in the air. So, so similarly, a beaker of water, if you raise the temperature, then it'd be similar to adding solvent, and you would be able to put more of the substance in. So that's another thing. Ooh, that was good. I almost left without saying that. That's 8A. There's an A and a B. And then 8B says, what would you do to change a saturated gas liquid solution? So it's a saturated gas liquid solution to an unsaturated solution. Well, let's see. You could, or I didn't write that, to an unsaturated solution. In this case, since I'm talking about temperature, you could decrease the temperature. You could shake it, because it's also has gas as one of its components. Then, as we saw up here, pressure is going to be an issue. So we could do something with the pressure as well. We could decrease, if we're increasing the temperature, no, that's for the other one. We're decreasing the temperature. That is inversely proportional. So you could decrease the temperature and increase the pressure. So that's what you would do in that case for number 8. Oh, and then finally a problem. Let's do number 9, and then we'll be done. And my phone is out of power. No, there it goes. Okay, so here's number 9. Number 9. I hope you have your book because I haven't been showing you the problems, but just reading them. Again, we're on page 524. And number 9 says the solubility of a gas is 0.58 grams per liter at a pressure of 104 kilopascals. What's the solubility if the pressure increases to 250 kilopascals at the same temperature? So this one's pretty straightforward. Again, you have S1 over P1 equals S2 over P2. We're going to be solving for solubility, the second one. So we're solving for this one right here. We want to get that all by itself. So S2, I don't want to do any shortcuts. So if you cross multiply, that's going to be S2 over P1, or S2 times P1 over or equal to S1 P2. And to get the S2 by itself, you need to get rid of the P1. So S2 is going to be equal to S1 P2 over P1. So what are all those things? Well, S1 is 0.58 grams per liter. Okay. P2 is 250 kilopascals all over 104 kilopascals. You can see the pressures cancel out. The solubility is in grams over liter. And where's the phone? 250 divided by 104 times 0.58.
It's about 1.3942.
1.39, how many sig fig? 332. So 1.4 is your answer. So 1.4 grams per liter is the second solubility. Ta-da! All right. So that's number 9. And so I didn't think we were going to be able to finish that, but we are, and we did.